I see there's a listing for a new machine language programming book on eBay, Machine Language for Beginners. Personal Computer Machine Language Programming for the Atari, VIC, Apple, Commodore 64, and PET CBM computers. No Spectrum. Goodbye. So let's do one other thing here, which is let's take a look at our machine code program in memory. And we're going to do that using the same method we did in our last video, which is by creating a simple basic program that runs a for next loop and prints the contents of memory locations for us. So let's go ahead and do that by typing 10 for f equals, and then we're going to start with our beginning memory location where our program is stored, which is 30,000. And then 2, and actually, so in this case, we don't know how many bytes of data our program contains, do we? So how would we figure out how many bytes of data our machine code program contains? Well, one way we could do that is by looking up the codes for each of these assembly language instructions, just as we did in our other video, to see how many bytes it would take up. But we can kind of figure it out by looking at the program here as well. So if we look at line 1, it says org. So the org is a command. So this command, org, should take 1 byte. And then 30,000, since that is a 2-byte value, or a 16-bit value, then that should take up 2 bytes. So line 1 should take up 3 bytes of data. And then in line 2, we have the LDA command, which, although this might seem like two separate parts, the LD and the A, as far as the Z80 processor is concerned, LDA is a single 1-byte command. And that's followed by the value FF, which is also equivalent to 1 byte. So line 2 contains 2 bytes. So line 1 has 3 bytes, and then line 2 has 2 bytes. So far we're up to 5 bytes. Now let's take a look at line 3. So similarly to the LDA command, the LDHL command also takes up 1 byte of data. And then we have another 16-bit value here, which takes 2 bytes. So line 3 also takes 3 bytes of data, similarly to line 1. So we have 3 bytes on line 1, 2 bytes on line 2, and then another 3 bytes on line 3. So far we're up to 8 bytes of data. And we'll take a look at line 4 now, which is LDHL with the brackets around it. And again, this is a single command as far as the Z80 microprocessor is concerned. So the LDHL converts into a single byte instruction in machine code. So that would be 1 byte, and then it's followed by the value of A. But this entire instruction line here takes up a single byte, which seems unbelievable because it's doing so much. But that's exactly why machine code runs so quickly, because it's able to execute these very simple commands without using up much memory. And that's also why machine code programs are good at saving space in memory, because here we have, which looks like a somewhat complex instruction that takes up only 1 byte. And just to confirm that, let's look that up in one of my old books here and see if that's true. So I just need to find a book that contains this LDHL, A command, which they all should. Okay, I found one here. I'm actually going to use, let me expand my window here a bit, so I can show you a bit better what I'm doing. So I'm going to use this book, Machine Code for Beginners, just because it has a very clear way of laying out the Z80 Assembly Language instructions. And so I want to look up that code, and I'll just go back to our program here, of LDHL with brackets around it, comma A. So let's find that code in the book here. And this book is actually quite useful because it lays out the different commands in different blocks here. You can see it separates all the commands into a way that is quite logically organized. So I want to look up LDHL, A, and here it is right here on page 44. LDHL, A has a code of 77. So you can see this entire instruction, LDHL, A, and the HL has the brackets around it, is equivalent to a single byte of machine code having a value of 77. So let's go back and take a look at the rest of our program now. So line 1 contains 3 bytes, line 2 contains 2 bytes, line 3 contains 3 bytes, and then line 4 contains a very impressive and almost unbelievable single 1 byte of machine code data. So here we're up to 3, 5, 8, 9 bytes so far, and then our final return command also contains a single byte. So that's 3, 5, 8, 9, and 10. So our entire machine code program contains 10 bytes of data. So if we go back to our emulator window here where we're entering our basic program, we need to look at 10 bytes in memory, starting at address 30,000. So that would give us a range of address 30,000 to 30,009. And then line 20 will say print F, which is the address, and then a comma, and then peek F, which is the contents of that memory location or address, and then line 30, next F. So if we run this basic program now, we should see our machine code program stored in memory. So we can see the result is not exactly as I expected, because I forgot that the org command is actually not an assembly language instruction. It's actually an assembler directive, which means it's not going to be part of our machine code program. It's only there to indicate to the assembler something we want it to do. In this case, we're telling the assembler where we want it to store our machine code program in memory. So this org command here is not actually a Z80 assembly language command. It's an assembler directive. So it's not going to be converted into machine code, and it's not going to take up any space in memory where our machine code program is stored. It's only used during the assembly process. So I forgot about that. So that accounts for 3 bytes of data, which if this had been a Z80 assembly language instruction, we would expect it to take up 3 bytes of data, 1 byte for the org instruction, and then 2 bytes for the 16-bit value 30,000. So that's kind of a stupid mistake for me to make, and I'm sure a lot of you were laughing at me as I was describing it, but that's okay. At least hopefully we learned something from that. So our assembly language program actually includes only lines 2 through lines 5, which would be 2 bytes and then 3 bytes, so that's 5 bytes, and then another single byte, which is 6 bytes, and then another single byte, which is 7 bytes. So let's take a look at our output from our basic program here. And we have 1, 2, 3, 4, 5, 6, 7 bytes, which is exactly what we expect now that we've discovered my mistake. And another way we could check this is by remembering that the last byte of our program will be this return instruction, which we know from our previous video contains a decimal value of 201. So if we look for the value 201 in our output, then we'll know that that's our return command as well, and that's the end of our machine code program. So there we see our machine code program in memory, and let's take a look at what this is telling us. So line 2, load A FF. This first byte of 62 represents the load A instruction, and then here's our 255, which we know represents FF, so that's making sense. And then the next line of our assembly language program is load HL 50,000. So then this 33 must be our load HL command. And then 50,000, since it's a 16-bit value, or 2-byte value, would encompass these next 2 bytes of 80 and 195 in decimal. So now we know that 50,000 in decimal breaks down into 2 bytes, which are 80 and 195. And 80 would be the low byte, and 195 would be the high byte, because as we learned in a previous video, the machine code program likes to have 16-bit values stored with the low byte first and then followed by the high byte. So we can easily confirm that by opening our handy dandy programmer's calculator here in Windows. And so let me just open that now, and we'll see if that's correct. So remember, we're thinking that this 50,000 decimal value is being converted into these two bytes, 80 and 195. So let's take a look. So we'll enter that value in decimal into our calculator, 50,000. And we can see here the binary equivalent of it. So here's our high byte, and here's our low byte. And our program over here should have the low byte being stored first, which is shown here as 80. And let's take a look at our low byte, which is 01010000. And we now know from our bits, bytes, binary, and hexadecimal video that we did earlier on that this bit should have a value of 64, and this bit should have a value of 16. So if we add 64 and 16, that gives us a decimal value of 80, which is what it's showing us over here. And then our high byte over here has 4 bits turned on, and these bits represent the decimal values 1, 2, 64, and 128. So if we add those together, 128 plus 64 gives us 192, and then we add 2 to that, which is 194, and then we add 1 to that, which gives us 195. And there we have our 195 right there. Perfect. Now let's just finish off our program here. The next assembly language instruction is LDHL, A. And remember, we discovered that this entire instruction takes up only one singular byte, which we just looked at in our book, which told us that that byte should be 77. And so why is our program showing us 119 if the book is telling us it should be 77? Well, the book is showing us values in hexadecimal. So I hope we're all appreciating the value of hexadecimal at this point, and also binary, because they're both critical, as we discussed, to know in programming Z80 Assembly Language and Machine Code. So if the book is telling us that hexadecimal 77 is the value that our basic program is telling us should equate to 119, let's just confirm that by going into hexadecimal mode here. And we'll clear this, and we'll enter the value 77 and see what comes up. And there we go. Decimal 119 is the equivalent of hexadecimal 77, which is what the book told us should equate to our assembly language instruction LDHLA. And there it is right there, 119, which is what the calculator confirmed. And then, of course, we all know by now that our final byte of 201 is the machine code equivalent of the assembly language return instruction. And you can click on that, or in the description I'll put a link to it for you there.